On September 5, 1906, in the beautiful town of Duino, Italy, a physicist by the name of Ludwig Boltzmann tragically took his own life by hanging himself, the reason being constant criticism by his colleagues for his belief in the existence of atoms.
Speak the truth, write with clarity, and defend it to your very end.
Boltzmann was born at a time when people didn't believe in atoms, but he was one of the first to use the concept of atoms and molecules to explain thermodynamics, a theory on which all engines work. Boltzmann also provided a correct formula for entropy, and his work laid the critical groundwork that enabled Max Planck and Albert Einstein to later develop the foundations of quantum mechanics.
Bei der Aufgabe, diese Gesetze, die experimentellen
I was greatly impressed by Ludwig Boltzmann's ideas, by which I was guided when formulating the laws I discovered during my experiments. He described entropy as the logarithm of the probability of the state of gases, starting from the atomic theory approach.
However, his revolutionary ideas faced fierce opposition from the leading scientists of his time. He had to spend much effort defending atomic base theories against his colleagues, such as Ernst Mach and Wilhelm Ostwald. This constant rejection led to a huge toll on Boltzmann's mental health. Eventually, Ludwig Boltzmann's gamble on the theory of atoms cost him his very life. Boltzmann's tombstone in Central Cemetery, Vienna, bears the inscription of his beautiful entropy formula, S equals K log W. Ludwig Boltzmann was born on the 20th of February 1844 in the capital city of Austria, Vienna, where he was educated privately until the age of 10. Boltzmann did his PhD under the supervision of Joseph Stephan on the kinetic theory of gases. It was Stephan who introduced Boltzmann to Maxwell's work on thermodynamics. Maxwell's work had a long-lasting effect on Boltzmann's scientific career, though these two scientists never met in person. At just the age of 25, Boltzmann was appointed a full professor of mathematical physics at the University of Graz, thanks to a letter of recommendation by his supervisor, Stephan. In 1873, Boltzmann joined the University of Vienna as a professor of mathematics. In Vienna, Boltzmann taught physics and lectured on philosophy, which became extremely popular and received considerable attention. Even though the largest lecture hall had been chosen for it, the people stood down the staircase. Boltzmann's career took off, working with famous scientists like Bunsen, Kirchhoff, and Helmholtz. Everything that happens around us, from the melting of ice to the expansion of the universe, raises a big question. Why do natural process occurs in one direction and not the other way around?
Very famous philosophy question. Why is the past different from the future? Why is there an arrow of time? Because the fundamental laws of physics have no arrow of time in them. The answer is entropy and the second law of thermodynamics. The universe used to be more organized, lower in entropy. The whole history of the universe is just entropy increasing, disorder and chaos developing all around.
We're all going to die.
It's not your fault necessarily, but you're contributing to the disorder and chaos all around us.
This was a central puzzle in the 19th century, as scientists were developing laws of thermodynamics. The second law, in particular, introduced the idea that entropy always increases in time. This time, asymmetry suggests a fundamental difference between the future and the past. Young Boltzmann was immediately hooked by this question. In 1872, Boltzmann introduced H-theorem to explain the irreversible nature of thermodynamic processes based on the mechanics of atomic particle collision.
Here is me in the Central Cemetery in Vienna, on the grave of one of my heroes, Ludwig Boltzmann, Austrian physicist, one of the greatest. Boltzmann developed the kinetic theory of gases, in which you are interested in the statistical properties of the gas, like the air around us or in any kind of situation, in which you don't want to look all the precise positions of the molecules of the gas, but the statistics of it, like the curve that is there on the right, on the top. Just below that curve is the Boltzmann equation, which describes with extreme precision the evolution of the distribution of particles. Think about this, because this is an amazing achievement. The particles all around us, these are all molecules, billions of them, all bouncing on each other in all kind of chaos, like in a fury, crazy really. And in spite of all this mess, the Boltzmann equation can predict with great accuracy what will become of these statistical properties, and you can use it. Boltzmann further devised the formula for the entropy, S is K log W, which is now written on his grave. S is K log W. W here is the number of configurations in which you can arrange your gas. For instance, if your gas is confined in a half box, this gives you much less possibilities than if it's spread all around the box. How many less possibilities? It's huge, huge number, much, much bigger than these attoseconds we heard about recently. Or than the debt crisis, of course. Now, Boltzmann also gave practical formulas for this. The formula you see at the bottom, minus integral f log f, is a practical formula for computing the entropy. This is a lot for a single man, and at the time of Boltzmann, not all his ideas were well understood. But later, his followers held him as a hero, like Einstein, Perrin, or Smoluchowski, people who used his work to prove the existence of atoms, that now we are know how to...
However, Joseph Loschmidt pointed out a paradox in Boltzmann's argument. If the underlying mechanics of particles are based on Newtonian mechanics, and therefore reversible, how can an irreversible process like the increase in entropy arise? To address Loschmidt's paradox, Boltzmann published a groundbreaking paper in 1877 clarifying the profound relationship between entropy, probability, and the number of microstates of a physical system.
We know the second law is true, we know that atoms exist, but exactly the right way to formulate these laws and to think about them is still a little bit contentious. So let's mention a couple of the objections. Loschmidt was a professor who was actually one of Boltzmann's teachers. So he was one of Boltzmann's mentors. He was on Boltzmann's side, like they were friends, they talked with each other. But he didn't really like Boltzmann's formulation of the second law at first. He came up with what is called the reversibility objection. It's a pretty simple thing. It's one of those things where, right place at the right time, you can get your name on something that is actually pretty simple. And he said, look, if you think about this picture, okay, let's just redraw the picture in a slightly smaller way. Okay, here's a smaller version of the picture. The underlying theory, the microscopic theory, is Newtonian classical mechanics. And a feature of Newtonian classical mechanics is time reversibility. There is no arrow of time in Newtonian mechanics. For every trajectory going one way, there is another trajectory going the other way in time. All you have to do is take momentum and go to minus momentum, typically, okay? So for every trajectory in phase space, with ds dt greater than 0, there's one, you can reverse it, that's why it's called the reversibility objection. There's one with ds dt less than 0. So in particular, if you say, well, I start here and I go out in various ways, depending on where I start from, there's an equal number of trajectories, like an exactly equal number, that go from high entropy to low entropy. So in the space of all trajectories, in the space of all things the system could be doing, it is equally likely that you would find the system increasing in entropy or decreasing in entropy. And that's not wrong. He didn't make a mistake, Loschmidt. And Boltzmann, argued against it. And it's funny, so I wrote a book about entropy in the arrow of time called From Eternity to Here. You're welcome to buy the book and read many of these historical details. Boltzmann responded in various ways. And the funny thing was, Boltzmann was always convinced that he was right, but the reason why he thought he was right changed with time. Even within a single paper, he would offer different responses to this. And so but we now have settled on more or less what the right response is. And the right response is there is a symmetry in Newtonian mechanics between going one way in time and going another way in time. That's time reversibility. So the coarse graining does not break. that symmetry, nor does the dynamics. We need something else to break the symmetry. If you want to claim to have an explanation for the arrow of time, Boltzmann thought he was just deriving the fact that entropy had to go up, and that's not true. He did not derive that, because Loschmidt was right. Entropy could go down in the space of all trajectories. What you need is a boundary condition. You need an initial condition for the universe. You need to break the symmetry, the time reversal symmetry, with a boundary condition. And this is one of the ideas that Boltzmann put forward. He said, he called it, Proposition A or something like that. The idea that at some time in the past, the universe started in a very low entropy state. That's it. It's just an extra assumption. It's not derivable from anything we've said so far. So David Albert has labeled this the past hypothesis. David Albert was one of the guests on the Mindscape podcast. We talked about quantum mechanics, but one of his most influential works was a book called Time and Chance, where he really laid out the logic of this situation. You need to be able to say that the universe began, I'm putting began in quotes and I'll explain why, in a low entropy state. So by that simple stroke of the pen, you simply eliminate all of these bad trajectories that are decreasing in entropy. You just say that you start here, and if you start there, then indeed you are very likely to increase in entropy. Okay, why do you have to say began in quotes? Because really what you need to make it work is that at some point in the history of the universe, not too long ago, the entropy was much lower than it is today, and by not too long ago we mean much shorter than the equilibration time for the universe, the time it would take to go from low entropy to high entropy. And indeed, this is true empirically. When we look at the universe, the past, near the Big Bang, 14 billion years ago, had a very low entropy.
Boltzmann was able to show that it was not that entropy always increases, but that it increases with extremely high probability. By introducing probability, his equation provided a statistical interpretation of the second law of thermodynamics. However, in all his work, Boltzmann needed to make a fundamental assumption: the existence of atomic or molecular-like particles that collide with each other to give macroscopic properties, such as pressure and temperature. This didn't go well with other leading scientists of his time, such as Mach, who rejected atoms as a physical object and only thought of them as a mere theoretical construct. Thus began a long and intense debate between Boltzmann and Mach camps over the reality of atoms.
Tombstone figured out what entropy is. It's the number of ways of counting the number of different microstates that correspond to a different macrostate. And we explain the arrow of time in the macroscopic world by two things. Number one, there are more ways to be high entropy than to be low entropy. So if you start in a low entropy state, it's very natural to evolve to a high entropy state. And number two, for some unknown reason, we started in a low entropy state. That's the past hypothesis that puts us there. So that's a very natural setup. We don't understand why we started in a low entropy state. That's what I was studying a few years ago. Today, we want to think about all of the ramifications of the fact that entropy is increasing. People like me believe that the fact that entropy is increasing is behind all of the different asymmetries of time in our real world, including cause and effect, but also memory.
Ludwig Boltzmann's position within his time's scientific community appears singular and somewhat isolated. In the late 19th century, a fierce battle was raging in the world of physics. The initial opposition to atomic theory can be traced back to Ernst Mach, a philosopher and physicist who was a prominent critic of the atomic hypothesis. Ludwig Boltzmann believed in the reality of atoms. Atoms were not just theoretical, they were real, fundamental components of matter. Ernst Mach, however, wasn't convinced. He famously stated during a lecture, "I don't believe atoms exist." Mach argued that science should focus only on what we can directly observe. Since atoms couldn't be seen or measured then, he rejected them as speculative. Mach's empirico-criticism philosophy emphasized that only sensory experiences matter in science. This disagreement wasn't just technical, it was philosophical. Boltzmann's realism and Mach's empiricism represented two different visions of science. their debate intensified, with Mach's followers, energetics, challenging Boltzmann's theories. The energeticists, led by the formidable Wilhelm Ostwald and Mach, believed energy was the fundamental substance of the universe, dismissing atoms as mere figments of the imagination. By the late 1800s, physics was dominated by the concept of energy. The energeticists, a group led by chemist Wilhelm Ostwald, believed that energy transformations were fundamental to explaining all physical phenomena. They saw energy as the cornerstone of reality, tracing their ideas back to Leibniz and Huygens. The debate between Boltzmann and the energeticists was intense and often personal. At the heart of the disagreement was a fundamental question: what is the true nature of reality? For Ostwald, it was energy, pure and simple. For Boltzmann, reality was built from atoms. Boltzmann, however, was not alone. Another giant of 19th century physics, Maxwell, was also a supporter of the atomics worldview. Indeed, Maxwell's pioneering work on the kinetic theory of gases deeply influenced Boltzmann's own development of statistical mechanics. The other Dutch physicist, Hendrik Antoon Lorentz, was also a supporter of Boltzmann's ideas. Lorentz read Boltzmann's papers with great attention and even applied them to the theory of electrons. Boltzmann was delighted by Lorentz's keen insights and willingness to engage deeply with his theories. Even after Boltzmann's death, Lorentz's admiration for him remained profound. In 1907, Lorentz delivered a commemorative speech for Boltzmann before the German Physical Society, stating, "The old doctrines about which Boltzmann speaks have blossomed, thanks only to his efforts, into a new and strong life. Even if their aspect has changed, and will certainly often change again in the course of time, we can hope that they will never be lost to science." Another influential scientific figure in the late 19th century was Max Planck. Planck initially adhered to the philosophical ideas of Ernst Mach and was not fully aligned with Boltzmann's atomic theory. Planck's perspective changed dramatically when he encountered Boltzmann's statistical mechanics while exploring black body radiation. As he studied Boltzmann's statistical approach, he became increasingly convinced of the validity of atomic theory. Planck then started opposing the energeticists, including Wilhelm Ostwald. Max Planck's relationship with Boltzmann evolved from initial skepticism to deep respect and influence.
Entropy, together with energy, is probably the most vital concept in nature. Energy remains constant. Entropy, instead, increases continuously. It can never decrease. This is exactly the essence on which the second law of thermodynamics is based. The entropy of a system of bodies may only increase. When brought to its maximum levels, it remains constant. If it increases, then the process is irreversible. If it remains constant, it is reversible and may even be inverted. This is the major difference between the laws of nature. Thermodynamical equilibrium occurs when entropy has reached its maximum level. If it does not increase, then no change can occur either. I was greatly impressed by Ludwig Boltzmann's ideas, by which I was guided when formulating the laws I discovered during my experiments. He described entropy as the logarithm of the probability of the state of gases, starting from the atomic theory approach. Successfully applying the adequate method to radiation fields could only be possible by considering radiation as also being made up of atoms, though still considering it as made up of special quanta. This theory inevitably created the assumption that they were atom beams, or well-defined dimensions of quanta, which are recognizable through measurements. At first, I was reluctant in formulating this hypothesis because it contrasted every classical atomic representation. Yet no other solution was possible. The study proved, thanks to the cooperation of many colleagues, that the theory was indeed true.
In 1905, a young physicist named Albert Einstein, just 26 years old, published 4 papers that set the stage for much of physics in the 20th century. One of these papers was on Brownian motion, where Einstein provided almost a direct proof of the existence of atoms, the theory Boltzmann holds so dear. Boltzmann was sent an early version of this paper, but any response from him remains unknown. Unfortunately, by that time, Boltzmann was already struggling with severe mental health issues, and a year later, in 1906, he tragically took his own life. Ludwig Boltzmann spent his final years defending his theories. He had a long-running dispute with the editor of the preeminent German physics journal of his day, who refused to let Boltzmann refer to atoms and molecules as anything other than convenient theoretical constructs. This just shows how worse the situation was for him. Boltzmann appears as a singular figure in the history of science. He was recognized by his contemporaries as a great scientist, but he had to fight for his ideas, which were seriously criticized. Boltzmann suffered greatly because he felt isolated and thought his ideas received little attention in Germany. His allies, Maxwell, Clausius, Stefan, and Loschmidt, had all passed away, leaving him surrounded by his intellectual enemies with no young physicists supporting him. He lived in constant fear of suddenly losing his mind and memory during a lecture, suffered from asthma and headaches, and was too short-sighted to read by himself. The mounting stress and sadness took a toll on his mental health, leading to delusions. Sadly, Boltzmann committed suicide on 5 September 1906 by hanging himself while on vacation with his wife and daughter in Duino, near Trieste. Although the energeticists' ideas were influential for a period, Ludwig Boltzmann's theories eventually proved more lasting and accurate. Shortly after his death, his ideas achieved wide acceptance with the help of Max Planck and Albert Einstein. It was a tragedy that Boltzmann did not live to experience the glory of his pioneering ideas. The discovery of the electron, Max Planck's black-body radiation formula, and Einstein's explanation of Brownian motion proved that Boltzmann had always been right. The energeticists' view, though influential, faded as the atomic theory solidified into the bedrock of modern physics. Besides physics, Boltzmann was also a philosopher known for developing ideas such as Boltzmann's brain and scientific realism. Interestingly, Boltzmann's statistical techniques are currently widely used in artificial intelligence tools for deep learning models, which goes by the name of the Boltzmann machine. Boltzmann was nominated 5 times between 1902 and 1906, though he was never awarded a Nobel Prize during his lifetime. His legacy lives on, even in death, with his most famous entropy equation inscribed on his tombstone.